teacher for the compulsory course, mechanical dynamics, 1 year. And then he retired in 2017, making a total of 30 years service in this department. But after that, he never, as I said, never left, never stopped working. That's what we call 退而不休. And recently, I noticed his paper and therefore invited him here with a very short note. He was so generous to agree on giving this special talk in our colloquium series. Basically, that's about newly discovered natural negative-refractive-index materials. So I will hand the microphone to Professor Hu. Let's welcome him.
Thank you for the invitation. Before I start, let me introduce my collaborators. Chen Zhiyu, who is now an assistant professor in Zhongyuan Christian University. Xu Mingjian, who is currently in Honghai Research Institute. Both of them earned their PhD in our department. And the last one is Lin Yuzhong. Perhaps some of you know him. He is a classmate of Professor Zhang Qingrui in undergraduate. All of this started with when, a few years ago, Lin Yuzhong walked into my office and said to me, why do we do something about energy momentum tensor anomaly in condensed matter? Then I know nothing about this anomaly, but I thought, since I'm retired, why not? Okay, so that started our collaboration. Well, actually, it's not the start of our collaboration, but that's this project. And Lin Yuzhong told me that if we have massless particles, then the trace anomaly will be manifest. And in condensed matter, there are massless electrons in Dirac center metals. So that leads to my outline of this talk. The first one is Dirac center metals. The second one is Negative-Refractive-Index. The third is the polarization function of Dirac center metals, and the result and conclusion. So at first I will introduce Dirac center metals. These three physicists say that Dirac center metal is a three-dimensional material where the conduction and valence band meet at points and are described by a three-dimensional Dirac equation. Actually, that's just you can view this as a three-dimensional graphene. Experimentally, people have found this kind of materials, such as cadmium arsenide, trisodium bismuth, and bismuth with a little bit of antimony, and other. I'll use the cadmium arsenide as an example to describe this Dirac center metal. This is the crystal structure, approximately. In practice, this unit cell will be very large, but it can be simplified like this. And this is the band structure calculated by first principal calculation. And you can notice that here's a band crossing over here, just at the Fermi level. And that what's give us the so-called Dirac cone. So this actually describes the electron dispersion relation. And the first principle calculation tells us that we are a pair of 3D Dirac cones. And they situate in the k-space. One is at minus kd and the other is at plus kd. The point is that they just touch each other so that there's no mass gap, or they are massless. And also, the dispersion near this point, which is called the Dirac point, is linear. And that's very important. Because of this linear dispersion relation, we can use Dirac equation to describe the electron in this area and in this area. In condensed matter, the effective Hamiltonian is like this. The P is the momentum, and the sigma is the spin of the electron, or you can say it's the Pauli matrix. And actually, one of this cone, actually both of them are doubly degenerated. So you can describe them with a 4x4 matrix. And the V up here is called the Fermi velocity. And this actually is the slope of this cone. To give you an idea, it's just 10 to the 6 millimeter per second. Okay. These are all what theorists say, but experimentally, you have to have some evidence, and that's more important than what the theorists say, right? So, here's the first experimental evidence I would like to show you is the result of STM. The Dirac points over here, or over here. And then the density of states of the electrons, which is proportional to di over dv, can be described by this curve. And this curve can be fit with the E squared, E is the energy, fit with the E squared forms. And that's the indication of linear dispersion relation of the electron. So that's a piece of evidence of linear dispersion relation of the electron. And then, of course, there's another, actually, more direct evidence. That's the angle resolved photoemission spectroscopy, ARPES. This experiment can measure the electron knocked out by photon, which is called photoelectron. And people can measure the energy of the knocked out electron and the momentum of the electron. And we can assume that the component of momentum parallel to the surface are conserved. So we can reconstruct the entire energy momentum relation. And this shows us that it's like a cone. The third evidence is that it's called Landau level spectroscopy with STM. If you put this sample under magnetic field, the orbital of electrons become Landau levels. And it can be detected by STM. And you can see that these dots are Landau levels. Actually, it's labeled here. And you can see that this is the evidence of linear distribution. And there are also so-called negative magnetoresistivity. Magnetoresistivity is defined as this: the resistivity under magnetic field minus resistivity without magnetic field. Negative means that when under magnetic field, the resistivity is smaller. And you can see that at least at the small magnetic field, the magnetic MR is negative. These are the angles of the magnetic field with respect to an electric field, because you have to apply electric field to have current. Now, this is a special signature of linear distribution relation and message electrons. We can see that because if you apply a magnetic field, then the originally doubly degenerated Dirac cone will be split up into two cones. Well, they're called wild cones, which means that one of them has chirality -1, and another has chirality of +1. And under the magnetic field, the electron state become Landau levels. This is a schematic plot of Landau levels. But notice that here's two special ones. That's n equals to 0 Landau levels. And they are straight lines, which means they have linear dispersion. So this direction is the direction of magnetic field. So the two cones split along the direction of magnetic field. And if you also apply electric field, then the electron can move from this Landau level to this. And the hole moves in the opposite direction. And this picture is same as a one-dimensional system. So you can just use the one-dimensional system to calculate the current.
Does the L and R have meaning?
Oh, left and right. It's a,
So, but this can be measured some way?
actually, L means chirality.
No, right. When you said it's massless Dirac, the natural thing is to distinguish chirality, but you did not touch it. So now you obviously put down left and right. So my question is about detection.
Oh, actually, you can see that left, which means that also helistic. If you electron moves in this direction, then spin direction is opposite to the motion. It's called left hand. And
well, I understand that, but
yeah,
so the field quoted, is it a theory paper or experimental paper?
This is a theoretical picture from the experimental paper.
So the question is, my question still is, have people detected these chiralities?
Yeah, sure.
I guess that's the degeneracy in that.
If you apply strong enough magnetic field, the energy will be different due to the Zeeman speed.
Okay.
So you can adapt it.
But this is actually wire fermion, and one is called magnetic monopole. One has a positive charge, the other has a negative charge. Yeah, which can be measured.
Yeah. So you can actually calculate the current very easily. This is the momentum change when you apply the electric field. And for the one-dimensional system, the charge, the changing rate of the charge of one cone is like this. And for 3D, you just multiply this by the degeneracy of the 3D level, and you will get this. So this is what you get negative magnetic resistance. First of all, it is negative, and then its magnitude is proportional to the cosine theta between electric field and magnetic field, and this can be measured experimentally. You can see that this is the angle. When angle is large, it's more negative. So that's actually a very strong experimental evidence of Dirac semiconductor. Okay, that's about it. So when me don't come to the office, and we decided to do something about this Dirac semiconductor, to look for trace anomaly in the condensed method. But it turns out that we got sidetracked because we find, in my opinion, more interesting phenomena. And this is Negative-Refractive-Index. Right? You call it Snell law, right? Ordinarily, both NY and NQ are positive. So this is the incident light and this is refracted light. But what if N2 is negative? Then this is the incident light, but the refracted light will be this way instead of on the other side of this black line. This is the experimental result. Means that they have been able to design and fabricate this negative index material. This is the ordinary material. You can see that the deflection angle is positive, but in their material, the deflection angle is negative. And this angle is negative. And you can also see that not all the frequencies give you this result. Only in the microwave range. Because the unit is a gigahertz. So why is the reflection index negative? Well, we can start with a very simple wave equation from Maxwell equation. Here, the epsilon is the permittivity, and the mu is the permeability. And the simple solution is like this. Usually we know that with this solution like this, it's an EM wave propagating toward the z direction. And the k can be like this, and the square root of epsilon and mu is equal to the refractive index. That's all very simple. The general physics level. Now, what if mu, epsilon and mu are negative? Then which side you can choose for n? Now, that's a problem. First, ask by Veselagov, who is a Russian physicist or Soviet Union physicist in the 1960s. So how do you choose the sign of this n when both of them are negative? Okay. Actually, it is related to the causality. Consider any response function, capital F, t minus t prime, where t prime is the time of you probe the system, and the t is the time of the system response, or the time you measure you take measurements. We must have t is greater than t prime because t prime is the cause and the t is the result. And that's what we related to causality. Now, so we have to require that when capital T should vanish if t is less than 0. Now consider the Fourier transform of capital T, f omega. Now if I want to do this integration, if t is greater than 0, then I can do this contour, and everything is okay. But when t is less than 0, I have to go this way. The semicircle will be in the upper half plane. But we require that ft is 0 when t is less than 0. So that means that we cannot have any singularity on the upper half plane. Now, the permittivity and the permeability are both response functions. So they must obey this kind of condition. And I just give you two simple examples, examples of the form of permittivity. Usually it's computed in this form, where omega b usually is called plasma frequency, and the omega 0 is usually the frequency of resonance. That means the energy level difference between the energy between two levels. So if I do a little algebra, I can get this form. And you can then remember we have required that epsilon will be analytic in the upper half plane, which means that the gamma must be greater than 0. And from this form, you know that the imaginary part of the epsilon will also be greater than 0 for positive omega, of course. But the real part of the epsilon can be either positive or negative. So we can write this permittivity in this form, right? And this phase phi will be in the range between pi over 2 and pi. Actually, it should be in the range of between 0 to pi, because in this range, the imaginary part of this is positive. But now we are interested in the situation where the real part of the epsilon is negative. So we restrict this phi in the range of pi over 2 and pi. All these can also be applied to permeability. So both of these phases are in the range of pi over 2 and pi. Now if we substitute these two forms into this form of refractive index, then we find that the refractive index has a phase which is also in this range. And the point is that the real part of refractive index is less than 0. So, how can we get the negative refractive index? We have to require both the real part of permittivity and the real part of permeability be negative. And of course, this will lead many interesting phenomena. Remember, this is our simple solution. Now, when k is equal to n times omega divided by c, when n is negative, then k is negative. Which means that actually this wave propagates to minus z direction. But on the other hand, the Poynting vector points to the plus direction, plus z direction. So the direction of k and the s are opposite. That's all right, because the Poynting vector points to the direction of energy flow, but the direction of k is just the direction of phase velocity. So that's okay. There's no contradiction. There are other interesting physical phenomena of this negative refractive index. One of our pioneers, Henry, said that you can make better lenses. If you just consider the lens maker's equation, this, and if A is negative, then you can use your imagination to see what happens. So first of all, usually the concave lens will become convex at resolution, and there are other many interesting phenomena. And also, when you detect the Doppler effect or Cherenkov effect, you will also find the reverse direction. This is because these two effects are also involved in the phase velocity of the light wave. And the last one is the visibility clock, which perhaps is more interesting to ordinary people, I think. This means that if you put an object in the orange area, and if you send light from left, and this is the negative refractive index material. Then this material will guide the light in this way, so that an observer over here cannot see the object in the origin area. This was actually had been made. The principle is like this. I'm a theorist, so I can only talk about principle. They use so-called transformation optics. Okay. This means that the light path in a medium with epsilon and mu can be transformed into the light path in a curved space. With the curve is actually in vacuum. So, if you want to hide something, you can put this thing in an area. Then, if it can be transformed into some curved space like this, and your object is over here, then you cannot see it. The reason why the negative refractive index material comes in is that in some of this area, since the epsilon and the mu are related to the slope of this path, then in some area the slope must be negative. So both of them to be negative are required condition. So, how do people do that? They use metamaterials. Metamaterials, actually, first of all, this is quite simple to make this negative, but not this one. So, what they use is so-called split ring resonators. It's like this. Here are several rings here. And actually, this just like RLC circuit. If you have magnetic field inside, then you already have reduced the current and vice versa. And you can see that here we have the opposite charge on different rings. That gives you capacitance. So this is just an RLC circuit. And the RLC circuit has resonance. Resonance is something like this. So you can choose your frequency so that this is real part is negative. So there are a lot of development of metamaterial to design this negative refraction index for NIM. But what we did, since we are theorists, we cannot do this kind of thing. We just do some calculation. But we find some natural material instead of metamaterial to have this problem. So we set out our work with this arranging things for this Dirac curve. Our original intention is that we was trying to see the energy momentum tensor anomaly in conventional matter. So what we did is we calculated the polarization function here. These dashed lines are photons. This is the polarization function. And this polarization function actually is related to the permittivity and the permeability in this form, where L here is the longitudinal part of this, and the T is the transverse part of this. But I will skip a lot of details of calculation. Those who are interested can find those supplementary material. So I jump to our results. Oh, actually, I forgot to mention, we did the calculation at finite temperature. It turns out that the temperature actually helps us a lot. Our result can be summarized in these two equations, where the C is just some smooth function of omega and k. So they are not crucial. The crucial part is this factor and this factor. Actually, they are same. We can see that this is a logarithmic function. And when omega is approaching VF times k, we have divergence here. And it's negative. So that means we can have negative epsilon and negative mu if we move omega close enough to VFK. So that's our major result. This is the curves we used previous paragraph to show you. The blue curve is the permittivity, and the green curve is the permittivity, and the blue curve is the permeability. The temperature is at 80 per milli-electron volt. That's about half of the room temperature. And you can see that in a very narrow frequency range, we have both these two punctual negative. If we raise the temperature to room temperature, which is beta equal to 40 divided by MEV, then you can see that the range of negative permittivity and the permeability are enlarged. So actually, temperature helps us. The higher temperature, the region of negative refractive index is larger. And this is the phase area. And the brown area, which is called phase 1, is where we have both epsilon and mu negative. And this is at this temperature. Now, we would like to apply our result to the real Dirac-7 method, which is we choose is cadmium arsenide. And we find this result. In the real material, there are many sources which can contribute to the permittivity and the permeability. But since this is not magnetic, so we only consider the other facts contributing to the permittivity, like atoms. The motion of atoms under electric field can create polarization. The polarization can contribute to the permittivity, and the contribution is positive. However, fortunately, our result shows that the negative contribution, the negative contribution comes from the divergent term. Therefore, no matter how large the positive contribution, we can also find a range where the negative contribution overwhelms. So this is actually our application. A brief summary is that Dirac method can be negative refraction index material, and this is a natural material instead of meta material. And the frequency range where you can find negative refraction index is approximately the temperature divided by 40, according to our calculation. That means for room temperature, the frequency range will be in the microwave range. And the negativity of both permittivity and permittivity comes from the logarithmic divergence of the polarization function. So the remaining question will be, where does this logarithmic divergence come from? Why other material cannot have this property? Our finding is that it is all due to the dispersion relation of electrons. First of all, the electron has linear dispersion. And second of all, their masses. Or you see, there's no mass gap. Or in condensed matter language, there's no band gap between conduction band and early dispersion. Let me use this graph to explain why the Dirac curve has this property. Suppose a photon comes in, it can excite the electron at A into the state at A prime. Then the same photon can also excite an electron at B to B prime. And it can also excite an electron at C to C prime. Because the energy difference between A prime equal to that of between B and B prime and between C and C prime. And also the momentum differences are also the same between A and A prime, B and B prime, C and C prime. So when a photon comes in, he saw a lot of opportunities to excite electrons. And that's what made the divergence so prominent. And that's the reason why if you have a Dirac curve, then we can get this negative refraction index.
So you can expect graphene to have the same property too, because graphene also has a Dirac curve.
Yeah, that's right. You see, the graphene, I think, also have this property. Though we did not do any calculation. But the difference is that for a two-dimensional system, it turns out that it's more difficult to get the analytical results than the three-dimensional. So you can try. Well, you try, students can try. So I think because in recent years, in condensed matter physics, there are a lot of hot topics which involve topology, and such as topological insulator, and this wire-7 metal, and the Dirac-7 metal. But my conclusion is that there's much more interesting physics beyond topology. Thank you.
Thank you. So I forgot to mention one thing at the beginning. That is one of the reasons why I invited him back. It was because this work was published on Physical Review Letters, and then later on highlighted by Nature Materials. So it's so simple but amazingly interesting. At least to me, I don't know how you feel, right? So I think all the graduate students, you can actually easily repeat the calculation here and found this interesting result. The issue would be the innovation, like another new idea just, you might share. So perhaps you or other students could try to do the calculation for graphene. All right, now I'm going to open the floor for questions. Yes.
One comment, one question. What you can do is for a microwave, very low frequency. As far as I know, this has been done in quite a few places. The difficult one is optical frequency. So dimping, and I'll try for that. And, now, one question. Your magnetic field here is just to transform Dirac fermion to wire fermion. Okay. But why don't you just start with a wire semi-metal rather than Dirac semi-metal?
Well, actually, we start with the simplest one. The Dirac metal is simpler than wire-7 metal because we can use a Lagrangian, which is in the textbook of quantum field theory, to do the calculation. And all the calculation can be automatically done, actually. Of course, there's a difference because we are using finite temperature formula. But in any case, if we start with the textbook Lagrangian, we can deal with those gamma matrices with a standard method, and we do not have to worry about anything else. That's why we use Dirac metal. For the wire metal, you have to break either the space inversion symmetry or the time reversal symmetry. Then in the Lagrangian, you have to add another term, which makes the calculation more difficult, more complex.
So you agree that your intriguing phenomena also appear in wire semi-metal?
Yes.
Okay.
Any more questions? From the students? Yes, there's one at the back.
Thank you. Thank you. You have mentioned that in the room temperature, the wavelength of the wavelength to induce the effect of Negative-Refractive-Index is in the range of microwave. So does it mean that the material with this effect should be very large and in a lot of kilometers?
A few kilometers.
就是蛮多波长比较长的，然后东西会比较大。应该不至于3 kilometers.
Well, actually, your sample need not to be so large.
It's a micron, isn't it?
Yeah. you can see that people have done this with the metamaterial, and these rings actually is very small. So you do not need to have a big sample. And this is done in the microwave image.
Thank you.
没有，我装电池了，这个好像没什么声音。
So you talk about this resonance effect, right? And but at least in those material looks like at least from calculation, and they're finite, right? And they're not infinite. Okay. So it's depend on materials and how many actually available. Right? It's a gold states.
就是讲话好像没什么，讲话没反应。
I know you tried to explain that, but it looks like the number of states still is finite, it's not infinite in the space.
Oh yes,
Right?
that's right.
And what's that impact to those phenomena? And the other thing is, the second question is, you know, this everything's relying on straight line on this Dirac cone. And what about, you know, and they don't actually meet at one point, but very small gap. And it's approximation. Will that also happen, you know, for those negative refractive index?
Thank you for the question. Okay. It's all are due to the resonance. You see, even if you have only one state, one pair of states as a resonance, you can already have some kind of divergence or singular behavior. But usually you have to take the integration, which means that if you have only one pair state which can have resonance, the volume in the phase space is really small, and then the divergence will be integrated out. Then you don't have any divergence. But here, we have a lot of states which have resonance at the same condition. That's why the divergence is very clear.
What happened if this gap opened up a little?
Oh, yes. When this is opened up a little bit, that's all right. Because, you see, we have, actually, we have done some estimation. Because here, actually, if there's a mass gap here, then we can see that I don't know whether you can see what I'm right on the record. So this thing will be replaced by this. So as long as the m is small, then at a certain temperature, this can still be negative. And temperature helps us a lot because at higher temperature, this is smaller and the more negative the magnitude.
So in this equation, how does alpha vary with this temperature?
Oh, sorry, I forgot.
This is not QED.
No, that's the QED. Alpha is the phi chart constant.
Yeah. So how sensitive it is to temperature?
No, alpha is not affected by temperature.
It's not function, it's a bracket.
Alpha is E squared over 2 pi.
It's probably it's alpha multiplied.
Yeah, not the function. You completely skipped the calculation. All right. Well, you did say how to calculate, but mass is QED. Having charge, and that's why I asked the question of alpha. I misunderstood, but there's a problem with it. So how do you do, for instance, renormalization, and do you really have massless electrons in the loop?
Okay. We all know that you have to regularize the results in QED, and fortunately, that job is for the time-independent parts. Here we have the time-dependent parts. So you see, for the time-independent parts, the denominator should be replaced by a infrared quantity, which is the lower bound of frequency. Well, actually, this is, I read it from the quantum field theory textbook. But at final temperature, the temperature replaces that lower bound. So we do not have to do any regularization for the infrared temperatures.
So do you know the behavior for extreme low temperature?
When temperature is really low, then the chance of negative-refractive-index will be vanishingly small. The higher the temperature, the better for us. Maybe I can do some explanation here. For higher temperature, this state becomes fuzzy. The distribution of the electron is also fuzzy. And actually you can have more state available for excitation and for the resonance. So that temperature actually helps us.
Okay, any more questions?
Can I have a
Sure.
comment, a discussion with the professor? One of the last statements, you said that there are much beyond topology. You mean, but okay, but this actually Dirac semi-metal and wire semi-metal are called topological semi-metal. So you are still willing topology. I mean, because the Dirac point, wire point is called topological nodal point, which if you circulate around, the very face is integer number multiplied by pi. And people consider this as topological semi-metals.
Right, but if you have a mass cap here, you will find a Fermi arc on the surface to connect the cones. But when you do not have mass cap, the Fermi arc is not important. It can be eliminated.
Mm-hmm. But if you have ideal wire semi-metal, I mean, for example, the normal transport is quantized. That's because you have one positive charge of one node and the other negative charge.
Right.
Yeah. So people still consider as a topological material rather than. Right.
Photo form the Dirac in fabrication. Photo form. how to form the fungi, how to form.
You
You have the
grow the crystal of the calcium arsenide. You just grow the crystal of calcium arsenide.
Well, go up to condensed matter center and ask Shankar to grow it.
You just grow the crystal of this compound.
Yeah.
Then you have to work on.
That's very complex. This phenomenon is very hard to solve. No?
There are just a few compounds.
So for your phase, the phase diagram, right? You have four phases, right?
Yes. I didn't explain that, right?
No, you didn't explain. Also, the diagonal line, that's the limit. Can I never pass that? The phase diagram?
Yeah.
This is a momentum space rule, right?
No. The phase 3 is both epsilon mu are positive. And this phase 2 is epsilon is positive and mu is negative. And over here, you do not have, of course, over here you do not have negative refractive index over here.
But then higher temperature.
Yeah, for higher temperature, this brown region will be larger.
So this is the momentum space rule.
The vertical axis is, yes, the vertical axis is horizontal K, which is momentum, and the horizontal axis is energy.
Okay, more questions from students? No? If not, then let's thank Professor Hu again. Yeah.
So I think it's a very typical characteristic among our students that you do have questions but never speak up. So feel free to approach Professor Hu before he disappears.
是啊是啊，但是现在听说司机鼓励的时候，应该有，应该有。
我在想说，
Maybe I can just give you the YouTube.
那到时候再请。因为我之前是有在名单上面看到，一定是超过说是后来
时间我们放在这里，东西到40分都还没到前面，是后来才退掉。
对啊，后来才退掉。所以那我现在要讲。
那反正就是当做现在要讲嘛，接起来现在我们
因为20分开始上课，实际上等到快30分，我是觉得今天后来也是这样，
但是我还没暂停。